At CBAF, scientists can advance our understanding of matter itself by probing the quarks and gluons in the atom's nucleus with beams of electrons from a superconducting accelerator. CBAF has an educational mission as well. The CBAF Science Series features scientists and engineers who are gifted at making their work not only informative, but fun. The Science Series is held once a month during the school year in the CBAF Center Auditorium. The presentation is live, spontaneous, and for the most part, unrehearsed.
Thank you. Welcome to the first program of the 5th annual CBAF Science Series. Again this year, we're delighted to have back with us the all-student camera crew of Newport News Public School Cable Channel 6, doing the video tonight in case there's an overflow audience, and making tapes available to interested teachers and others to borrow after the program. We're very lucky to have actually a quite diverse set of programs this fall, which include physics and even biology. Something we haven't gotten into a lot at CBAF, but I think you'll find the programs very interesting, and they're flyers if you haven't gotten them out in the lobby. We're really delighted to have with us this evening Dr. Gina Rameika. Dr. Rameika is an experimental physicist at Fermi National Accelerator Lab, or Fermilab, outside of Chicago, Illinois. She grew up in New Jersey, got her bachelor's and her PhD degrees from Rutgers University, and while she was a graduate student there was the first time she went to Fermilab as an experimental researcher. She's married to another physicist and has 2 children, a son aged 9 and a daughter aged 5. Her topic tonight is rather Shakespearean, Much Ado About Almost Nothing, or the science of very small particles, including especially the elusive neutrinos. Join me in welcoming Dr. Rameika.
Hi, can you hear me? You should be able to. I've never been so wired up in my life. I've also probably will never be under so many lights or cameras for the rest of my life. So this will be a real experience. Most scientists usually work very quietly in laboratories and don't get under, this kind of exposure. So pardon me if I'm just a little nervous. It sure tells me I'm glad I didn't go into journalism. I don't think I would have survived that. But I think before I start, I'd like to tell you a little bit about how I came to be doing what I am, which is physics, and in particular elementary particle physics. Because unlike, for example, my husband, who I think probably from the age of 6 wanted to be a scientist, and by the age of 10 knew that he wanted to study particle physics, I was quite the opposite. In 8th grade, I hated science. I really didn't even know what it was, because the only science we had ever done in the school I went to was collect some rocks and make a map of the solar system. So that didn't really get me very far in liking science. In 11th grade, I slept through chemistry, and I was lucky I had the first period class, and my seat was up against the bulletin board, and so I was able to put my head there and just sleep through for about 50 minutes until the next class started. But the next year turned things around a little bit. I went to a physics class, and that was kind of exciting, mostly because the teacher made it exciting. We rolled balls down inclined planes and predicted where they would hit the ground. And the power of being able to predict something seemed rather fascinating. And so I decided I really liked physics, but I guess I was inclined more to one of those careers that your parents tell you might be good to do, like become a doctor or become a lawyer. Do something that'll make you a lot of money, and go to college and study hard. So I decided to go to college, and I would try to become a doctor, a medical doctor. And at Rutgers University, that's what probably 2/3 of the entering freshman class decide that they're going to study as well. So you get there and you're told the first day, 2/3 of you want to go to medical school and probably 1/10 of you may make it. You better think this through again. And I was pretty determined that I still wanted to do it, but I thought I'd kind of sneak around the system. And I majored in physics because they tell you when you try to get into higher level schools, they look for diversity, kids from Alaska or Timbuktu, or people who major in strange things. And so I decided not to take the standard pre-med classes, but instead stick with this physics, try it out a little bit. And I'd take a minor in some of the biology and chemistry. And the first year I did that, I took physics, I liked it. The second year I started taking those biology and chemistry classes, and they were pretty tough. I didn't particularly like that cat they made us cut up in the anatomy class. And meanwhile, the physics I was doing became more and more interesting. And the reason it did was because you thought about what you were learning in the biology and the chemistry classes. And in biology, you learn about cells and you learn about what's inside them. The cells are made up of molecules. The molecules are made up of atoms. And in chemistry, you learn about the atom. And you learn that the atom is made up of protons and neutrons. And in physics, you start to ask even more questions, like what's the proton made up of? And it's kind of like one of those dolls. If anybody's seen those stacked dolls from Russia, they could be very big, and you take one off, and there's another one inside, and you take it off, and there's another one inside. So you keep probing. You go deeper and deeper and deeper, and there's more and more to it, and you never really get to the bottom of it. And I kind of like that. It was a real intriguing puzzle, and I just couldn't stop studying it. And hence, through the years, through college, I stuck with physics, ended up being persuaded by a professor to come out and visit this place called Fermilab, and I got there and I fell in love with it. Now, in the course of this talk, I hope to tell you a lot more about Fermilab and what we do there. But to start with, I also, to give you a good feeling of what we do in particle physics, that puzzle that I hope some of you picked up on the way in sort of says it all in the sense that we ask how the universe works. Did everybody get one of these? If not, we can get more if you didn't pick one up. But the fact is, you ask how the universe works, and what that means is we ask basically two very fundamental questions. What is the universe made of? And what are the forces that either hold it together or blow it apart or keep things in order? And as I said, you look at particles, you start with the very big, macroscopic, the big things, and you go deeper and deeper and deeper. But you're never really sure if you've seen the smallest thing. What you do is you see things in a laboratory, whether it be a biology lab under your microscope, or in a chemistry lab in your test tube, or in a physics lab that I'm going to tell you about, but you don't know if it's the smallest thing. And the other thing you start to do when you investigate smaller and smaller structure is you start to see that you may be missing some things. There are certain things that you never see. Okay? For example, in this puzzle, if I tell you that these represent, I should use this pointer again. For somebody who works at a lab, like you'll hear about at Fermilab, I'm not very good with the high-tech equipment here. There. Okay. So if I tell you that I've observed things like these, and these are made of what are called fundamental building blocks, I can study them and try to figure out what the fundamental building blocks are. And I also say, I never see something like this. I never see a big triangle. I never see a big square. I never see an S with no pointy ends. So what I don't see is probably as important as what I do see. And I have to always remember that when I'm studying and probing deeper and deeper. You can't just believe the things you see. You've got to ask lots of questions, like what am I missing? Okay, so let's put this aside and we'll come back to it before we finish. Of course, if you kind of get bored with what I'm saying, you can stare at it a little more, try to figure it out. And we'll see if people can come up and tell us what the answer is. But what I want to talk about is what I do in particle physics, which is trying to discover the building blocks of matter. Now, you may remember or recall from history or ancient history that even the ancient Greeks asked the question, what are the fundamental building blocks? 400 years before Christ, the Greeks had a theory that there was a very fundamental particle, and they called it the atom. It was the thing that was indivisible. You could break things down smaller and smaller and smaller, and eventually you would get to a very fundamental particle of which everything else was made of. Now, the Greeks were very advanced, and they thought a lot. Then civilization goes through its ups and downs and don't make a lot of progress sometimes for thousands or hundreds of years. But let's kind of bring ourselves up to about the middle of the 18th century when there was a pretty well-developed science called chemistry, and people had observed that the world was made of things called elements. Okay? And then as we move through from the mid-1800s till now, we've progressed, and I'm sure everyone's familiar with these terms. We've got the elements, they're made up of atoms, atoms are made up of nuclei, and nowadays we talk about quarks, and we're going to get to a little more detail on that. Now, it's really true, though, that the world around us is made up of the chemical atom. And they say, I slept through this class, so I don't know too much about what's on this table. But if I have to use it nowadays, I do know where to find one of these in the encyclopedia or a research, a reference book. But this is the periodic table of the elements. And from about the mid-1800s, through the mid-1900s, people filled this table in. They found that there were many, many elements, very basic elements that made up nature. And they had patterns starting with very, very small atoms up to very, very heavy ones, and you could arrange them. And this periodic table was an attempt to put order into the world around us. And it's quite an accomplishment to this day. I mean, the field of chemistry is vibrant, and many, many discoveries come out of studying the way elements interact with each other. But as I said, I got kind of intrigued by probing deeper and deeper. You know, what was the chemical atom made of? And that became more or less the topic of discussion as we entered the atomic age, where people became quite comfortable talking about protons and neutrons. The chemical atom was made up of protons and neutrons. And as I showed you, it ranged from very, very light elements, like hydrogen, to very, very heavy ones, like uranium. And these other little particles had to creep into the picture. Going around the nucleus of the protons and the neutrons, there were electrons, and that made up the atom. And then sometimes the electrons or the atoms would radiate and light would come out, and these were photons. So although we had a very nice picture of matter in the chemical element, it was obvious that this atom was much more fundamental. It was also very, very small. A typical atom is very small, like 10 to the minus 8 centimeters across. And that's a lot of zeros. And it weighs very, very little. 10 to the minus 24th grams. Look at all those zeros, okay? I mean, these are really, really small. And these are what go together to make up things that are really, really big. So this is quite intriguing, and turns out it gets quite difficult to study. But again, just like we thought about the chemical atom, we always see the building blocks are very, very small. But you've got to remember that's what makes up the world around us. So if we really want to understand the world around us, we have to understand how pieces interact with each other. Okay. Now I just want to remind you, remember that table again. I remind myself of this. Okay, if I have a table on the periodic table, an element, it has a certain number of protons in it. It has a certain weight. Most of the weight is made up by the protons and the neutrons. Okay, I just want to remind you of those two numbers, protons and protons plus neutrons, making up the weight of an atom. Because I'm going to come back to that in a little while. And the reason we're going to have to come back to it is because although we know all about those chemical elements, and some of them are very stable, the things that we use every day, hydrogen, carbon, many, many elements. Lots of them are not stable, okay? Okay, what does that mean? Okay, now I'm going to stick up here a chart, and I don't want anybody to think they have to really follow this chart. But I want to introduce a term, okay? And I'm sure you've all heard of it. I mean, everyone's heard of the terms of radioactivity. But those elements on that periodic table, especially the heavy ones, are not stable, and they decay. They're not the things that your chair is made of or your floor is made of, okay? They're elements that are observable or created in the laboratory, and they don't stick around very long, okay? So what does that mean? Well, they actually, what I want you to remember is they can decay in two different ways. One is called an alpha decay, and the other is called a beta decay. Now, an alpha decay just means that an element like thorium, it has an atomic weight of 232. That means it has a combined sum of protons and neutrons of 232, and it has 90 protons, okay? Now, it can give off what's called an alpha particle. Now, that's really not all that complicated. What it is, it's an element like helium, which is 2 protons and 2 neutrons. But if it gives it off, it then becomes radium, okay? So it's lowered its atomic weight, and it's lowered its atomic number, but there's another particle floating around. So if you had to count everything that was there, you start with this, and it has a reaction to this element plus that. Okay, that's fine, and that was discovered, that process was discovered in the early days of the atomic age, which was about 100 years ago. Now, something happened as well. This thing called beta decay. A nucleus like lead sitting over here, okay, it has an atomic weight of 212. That means the sum of the protons and the neutrons make 212, and it has 82 protons. It is observed to decay to bismuth. I think that's bismuth, but if I get it wrong, I say, remember what I told you about chemistry. I don't know these things too well. I like protons and neutrons. They're much simpler, as you'll see. But it decays to this other element plus an electron. Now that's fine. The process isn't that different than the other one that I described. But there's a famous law, which I am sure that all of you will recognize. Right? Remember that E equals mc squared? Okay. Well, let's just talk about the E. That's the energy. Energy must be conserved. Okay, that means, if I go back to this little reaction here, if I start out with this lead, and I turn into this other element, and I have an electron, if I add up the energy that I started with, okay, that this guy had, and the energy that this had, and the energy that this has, because now, to be honest, it's a little more complicated. These just don't sit there and kind of decay. This thing may be sitting there, but when these go off, they move off in a direction. And what happens is, scientists who study this noticed that the energy wasn't conserved. If they added up how much energy this guy would carry off and this guy would carry off, it didn't add up to the amount of energy they started with here. Now that's a very difficult problem if you honestly believe that energy and also what's called momentum is conserved. Now this was studied, we're talking now about the 1930s. And this perplexed the scientists, and they were really, really worried. Did they have to throw out a very fundamental law that everyone believed, that energy was conserved? Well, here's where we get to my favorite particle. And there was a scientist named Wolfgang Pauli in the early 1930s who postulated something rather crazy. I mean, if I had been around then, and it's true, a lot of people just did not want to accept this concept, he postulated a particle. Now this is pretty tough. Inside that lead nucleus, remember there were a lot of protons and neutrons. He says
one of the neutrons changes into a proton, and that could actually be proven. That electron, we could see it went carrying off, but remember there wasn't enough energy? The energy didn't add up. He says, well, there's this little particle that came out with it. And everybody said, sure. This little particle had no charge. It couldn't be detected by the way you would see the charge electrically on these guys. It had no mass. You couldn't weigh it. Okay? It didn't make up anything. So it's really nearly undetectable. But it's a good explanation. If this exists, it could be the thing carrying away the missing energy. Now, this was not an easily accepted hypothesis. And many people wanted to believe that, well, there may be something to this theory, but it's mathematical and there's something else hidden. There's something else going on. Because, would you believe it? It's hard enough to believe in protons and electrons and neutrons. Remember how small they were. Well, it turns out that scientists are often willing to believe a lot of things if they explain what they've observed. And you may believe something for a very long time if you don't observe or figure out something else to take the place of that theory. Well, it turns out through the years that there were ways to prove that Pauli was right. One of the more interesting ones actually leads us to another little topic. The sun. Now, the sun is a pretty important star, right? What's the sun made of? It's made up of gas, very, very hot gas, mostly hydrogen. Turns out that inside the sun, there's lots of hydrogen, there's lots of protons bouncing around at extremely high temperatures, lots and lots of energy. And there's a very complicated cycle going on, which I'll show you in a minute, but it's not all that important. What's important is that you can write down the process for the sun, and in that process, because you believe that energy is conserved in all the reactions that you write down, you can write down a process for what goes on in the sun, and it involves both the alpha and the beta decays that I talked about, and it says that the sun produces neutrinos. In the reactions in the sun that produce the energy, now most of the energy of the sun that we know about, that we think about, that affects our everyday life, is that thermal energy that heats the Earth, and that's 97% of it. But it turns out that if you write down a theory of what goes on in the sun, 3% of the energy created in the sun would be carried away by this particle called the neutrino. Right. Now, if you believe that, you're pretty, the process is very complex, because I wouldn't believe that I just could write down an equation and say that there were 2 neutrinos. But it turns out that scientists who study the sun, mostly astrophysicists, chemists, actually have done a lot of work. They really know detailed processes that go inside of the sun. Now, no one's been there. You can't really get in there. All you can do is observe the sun. You can watch it cycle. You can measure sunspots. And you study it. You model it. Okay? But if you write down all of this, I say the bottom line is that you produce neutrinos. Now, the reason people studied those processes is because they really do want to know how the sun works. How hot is the sun? How much energy does it put out? How long is it going to be there? I mean, that's kind of a relevant question, although it turns out when you figure out the answer, none of us have to worry about the sun going away. But part of wanting to understand all of the world around us is that we develop a solar model. We really do want to know how the sun works. And if this theory that we just wrote down, if this whole chain of reactions that we believe goes on inside the sun, but we can't get there to measure them, it would be nice to detect these neutrinos. Okay? Now, that's a good one. Remember, this neutrino has no charge. It has no mass. It's almost nothing. The sun is 93 million miles away. Okay? You ask, how many of those neutrinos should be there? Well, it turns out that there should be, if that model that I talked about was correct, what is it, 60 billion in an area this big, that's a square centimeter, every second are coming from the sun down to the Earth. It's called the solar neutrino flux. Okay? Now, if you ask me if they're even wrong by a factor of 2, that's still a lot of neutrinos. It would really be nice to detect them. Now, if I were you, I would be asking a lot of other questions before I asked how would I detect them. Some of them you might ask is, how do we really know that these neutrinos exist? So far you've just told me that they've been postulated as something to explain an equation that doesn't balance. So how do I really know they exist? Can we detect them? If they have no mass, they have no charge, how would you ever expect to detect them? And how do they interact with other things? If there are that many hitting the Earth every second, why don't I feel them? Why don't I see them? Why don't they do something to me? That's a big number. Okay? Now, it turns out the neutrino is probably the strangest of all these particles that we have to deal with. The proton, the neutron, the electron. We'll all accept that the atoms are made of those, and we're actually lots of tests you can do. But the fact of the matter is, because we ask those questions that I just put up there, particle physicists get into the picture here to ask about the neutrino, how to understand the neutrino. So what we do, I should tell you that the people studying the sun, as I said, were astrophysicists and the like, people who deal more in chemistry and big macroscopic things. The particle physicist comes in and says, I'm going to try to understand that very small particle. Now, the way we're going to do that is we're going to ask, I want to understand the proton, the neutron, and its associated relatives, but I need a tool. The tool is called an accelerator. Now, you have an accelerator here at CBAF being built. Where I come from at Fermilab is called the National Accelerator Laboratory, and I'd like to just take a few minutes and show you what that looks like. I hope you can see it. Okay, this is our site. We're 30 miles west of Chicago. This is our high-rise building, similar to the building you're sitting in now. It's 15 stories high, sitting above the Illinois prairie. So as you come from Chicago, it doesn't take very long before you actually can see this building, because everything else there is very, very flat. So we have a 15-story central laboratory, and this is a 4-mile circumference accelerator. Okay? Now what does that mean? Let me show you just a little bit more detail. That big complex starts with this very, actually, futuristic-looking machine. It's called a Cockcroft-Walton accelerator. There's a person. This is the size of the very first stage of an accelerator. Now, sitting off to the side, what happens is a very small bottle filled with hydrogen injects hydrogen atoms into this very large machine. And the point of this machine is these are electrostatic kickers that will accelerate just gas sitting there, hydrogen gas, to 750,000 electron volts. Okay? And it's hard to say what that is, but they're moving pretty fast. They're moving fast enough that we inject them into another accelerator that makes them go even faster. This is called a LINAC. And this has kickers along the way. So now little hydrogen atoms are getting kicked faster and faster and faster down a line. Okay. Now, they've been kicked down a line over here. That's where that tunnel I just showed you was kicked down a line into what's called a booster. That's another accelerator. Okay, that makes them go up to what's called 8 MeV. And from the booster, they're injected into the big 4-mile ring. In the 4-mile ring, they're injected up to first one ring, which I have to show you. Inside that 4-mile ring, this is a tunnel. Like I said, it goes 4 miles around. It has 2 layers of magnets in it. In this magnet, this string of magnets, the particles are injected up to 150 GeV, that's giga electron volts. Remember, they started at 750,000. Now they're at, try to remember how to do it. GeV is like 1 billion electron volts. So now these are 120 billion electron volts. You go around the tunnel many, many times till they're injected in the bottom tunnel, where they go up to 800 billion electron volts. So the energy of the protons is raised higher and higher and higher until they're near the speed of light. After that, we're going to do physics with them. Now, if that was very confusing, I'm going to try and make it a little bit clearer by something I brought from home, done by real professionals in this business. And I think Steve is going to set it up for you.
Space and energy and the Big Bang. Molecules, atoms, particles, tiny planets and stars, galaxies mighty. Is everything so different, or is it all the same? Can we find the rules to learn to play this game? Searching for the answers to the questions we ask. And what will be the tools to help us with the task? How can we? Are you and me too small to see? How can we understand? With the help of accelerating science, 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 science. Theories that resolve accelerating science. Questions to ask accelerating science, 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 science. People using machines accelerating science. Science, people, technology. Very short time. Next comes the booster in a tunnel underground. The booster is a synchrotron. Notice that it's round. A proton's accelerate is soon to be revealed. Every time around, pushed by an electric field. In the synchrotron keep the beam on course. Currents in the magnets produce the bending force. The more we push these particles to near the speed of light, their tiny mass increases much, their speed but only slightly. The next accelerator job of these two rings, holding antiprotons for doing collider rings. The cryogenic teletron's an energy-saving hero. Its superconducting magnets have resistance nearly zero. Protons to fixed targets, or if we should decide, with antiprotons where they will collide. Detectors, computers, and human intuition combining together, making sense of these collisions. Seeking out these mysteries is what we try to do. This is just a start. The rest is up to you. Microscopic but gigantic, increasing resolution, curiosities around us, approaching new solutions, collecting information on this journey we travel. Secrets of the universe beginning to unravel. What we need to see is more than you and me. We have a way we can understand. With the help of accelerating science, 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 science.
Okay. I'll tell the people at home that made that you clapped. You can see that some of that was a lot of just the fun things around Fermilab, like the buffalo, the geese, and so on. And this is an open invitation to anybody in the Chicago area to drive 30 miles west and come out and see us. We're open to the public, and we have tours 7 days a week. You take a self-guided tour. You go up to the 15th floor of that building, and you can look around and see everything, and there's always lots of physicists around willing to answer questions. So it may be fun, especially if you find this intriguing. Now, I don't know if you remember in there was a picture. I just want to give you an idea. Remember, we're looking at the smallest particles in the universe, and it seems like we need the biggest machines in the universe to do that. And that's just the way it goes. There's a person right in there. This is called our collider detector at Fermilab. And in this accelerator, this is when the accelerator comes through with protons in one direction, antiprotons in another. They collide. That's matter and antimatter. Remember, Star Trek and the anti-universe. It's not quite like that. But you do need a big detector like this to see all the things that come out. The way I like to describe it, I draw a much simpler picture. You send a proton in, you hit a nucleus, lots of things come out. And the more energy that you can put into this proton, the more new and exciting particles that can come out. Now, it turns out that Fermilab right now is the largest accelerator in this country studying particle physics. But accelerators have been around for a long time, maybe since the 1930s when people started trying to study particle physics. They started out small. They used to be able to sit on the size of a table, and they got bigger and bigger. So the bigger the proton energy got, the more and more types of particles that came out. At first, they would just scatter the protons and neutrons, and scientists were able to study different things about the particles by the way they scattered and so forth. But about the middle of the 1960s, these accelerators had enough energy that they were creating lots of new particles. Now, so far we've only talked about the proton, the neutron, the electron, the neutrino. But if you put a lot of energy from an accelerator into a collision, you can produce a lot of other particles. These are kind of called strange particles. And if you've been following the news, every now and then they mention discovery of new quarks. They're sometimes called bottom particles or the top quark. Turns out it's quite complicated. And for people who got into this business to try to figure out what the fundamental building block was, they created a whole lot of new particles. And it was beginning to look more messy than the periodic table of the elements. It was like there was no order to this. They called it the subatomic zoo. We could just put more and more energy into these machines and create more and more of a mess and more of a complicated situation. And only a little bit got to know a little bit better what went on inside the proton and the neutron. So of course, scientists do like to stay organized a bit. Sometimes they look scatterbrained, but the big question of the day, was there any order to this zoo? Okay? And it turns out in the 1970s, the order emerged. And it's called the Standard Model of Elementary Particle Physics and their fundamental interactions. And what really comes out of that theory is what I call a new periodic table, okay? And that's good, because remember again, I didn't like that chemical periodical table. There's too much there to remember. And the new table is quite simple, actually. But we do have to deal with a little bit stranger things. Namely, yes, we are studying matter, and that's what the world around us is made of. But there's also antimatter, and that's very real. You can create it in those collisions. Antimatter is just like matter. Okay? For every quark, which it turns out the new order came out to be that protons and neutrons were made up of quarks, the up quark and the down quark, that electron that we've discovered floating around the atom, that neutrino that explained the missing energy, there's your real world. Everything in your real world is made out of this column of the new periodic table. But those accelerators that created all those new particles, and lots of particles, turned out to be made out of only these building blocks. Okay? Now, you notice this is the electron and the neutrino. This is the real world. There's a symmetry here, but you only make the symmetry in super high energy collisions. But the fun thing is, and we'll get back to this in a minute, but the electron has some cousins. Okay? They're called the muon and the tau lepton. Now, these are actually detected in high energy collisions. When you make some of those strange particles that you don't see in your everyday world, they decay. They don't live very long. Just like those heavy, unstable nuclei don't live very long, neither do the particles that you create in an accelerator. They don't live very long. They decay. And just like when that nucleus decayed and gave off an electron, and presumably this neutrino, these new particles that we create in the accelerator, they also decay, and sometimes they give off an electron, a muon. It's a cousin of the electron, and a neutrino that goes along with it. Because the same thing happens when we're looking at these strange particles. They couldn't balance the energy. There was more energy to start with than they measured in the end. And so not only do we explain the real world this way, so we explain the subatomic world this way. And so particle physicists created this new table to explain the structure of matter. Okay, that's fine. But meanwhile, we still have that problem that this neutrino, we can't detect it. Okay? Well, while all the accelerators were being built and all the particles were being discovered and this table was being put together, there's a lot of physicists in this business. And, you don't need all of them studying all the same thing. They kind of spread out and do different things. Some of them studied neutrinos very, very carefully, and this was very, very hard. But what they learned over the course of 30 to 40 years, that the neutrino does interact, but it's very, very weak. As a matter of fact, the way it interacts is the weak force. Now, I'm not going to go into a lot of detail about it, but what I'm going to tell you are two things. One is it interacts very weakly. By weakly, I mean the probability of it interacting in material. And these are data curves. Turns out if you can create neutrinos with higher energy, the more energy you can give them, and that means if you can create them in an accelerator, you can give them a lot of energy. The more energy they have, the more probability they can have of interacting. And if you can make them hit something very, very heavy, you also have a higher probability of interacting. So what these curves are data curves taken by scientists studying neutrinos, where they create neutrinos, they try to make the neutrino hit a hydrogen atom and produce a signal, or a helium, or carbon, or oxygen, or iron. Now, if you know your chemistry, you'll know that these are heavier and heavier materials. So, although the neutrino interacts only very weakly, if you interact it in a very heavy material, you have the highest probability of detecting it. Now, talk about what do I mean by high probability? Not very much. This is a number called the cross-section, or it's related to the probability that you could detect it. Can anybody see that number? It's called 10 to the minus 38. That's pretty small. That's a decimal point with 38 zeros and then a 1. This is beyond the comprehension of most people. Remember, the mass of the proton was 10 to the minus 24th grams. Even that's pretty small. I mean, you could never imagine that. This number is very, very small. Now, if you remember the number I told you, remember how many neutrinos were coming from the sun? That was 60 billion. Okay, but that was only 6 times 10 to the 10th. Okay? So if you had that many and you had a probability of seeing it, if you could put them together, maybe you could see an interaction. Problem is, even this number is a whole lot smaller. You multiply this times the big number. If you have lots and lots of neutrinos times a very, very small interaction probability, if you can get the number like 1, then that means the probability that you're going to see it is there. Well, this is very hard to do. Neutrinos are very, very small. But I want to come back to my solar neutrinos and tell you that people don't give up just because something's hard or very small. And there's a very classic experiment that was set up to detect the solar neutrino. Now, this is a place I'd like to visit if I ever get out there, and I know that they do take visitors around as well. It's the Homestake Gold Mine in South Dakota. This is a very classic solar neutrino experiment begun in the early 1970s. And the idea was that everyone had that theory that the neutrinos would come from the sun. There was a gold mine nearly a mile underground. A group of physicists decided that if they could go, they would go down underground and they would build a big, big container for, and again, this is a chemical problem for me, but what this is perchloroethylene or dry cleaning fluid, okay? They filled a tank with 100,000 gallons of dry cleaning fluid, okay? Now, why would you do that? Well, it turns out because the chlorine in that fluid is sensitive to neutrino capture. So if a neutrino came in, it could hit a chlorine atom, be captured by it, convert to argon. If you could detect the argon, you would know a neutrino came in. Okay, now, first thing I would ask is, why did they have to go underground to do that? Okay, now, first of all, it's not really a problem going underground. The Earth isn't going to stop the neutrino. That's the one thing that's interesting. But other things, if something else came in, like an electron or a cosmic ray or particles floating around just in the atmosphere came in and hit their chlorine and made this reaction occur, then it would invalidate the idea that the neutrino came from the sun. So what they do is they go down a mile underground where nothing can get to the tank except something that's able to penetrate a mile of Earth. The only thing that can penetrate a mile of Earth without being stopped or interacting in other things is a neutrino. So that's the idea of the experiment. And as I said, remember, they've been there for 20 years doing this. Why have they been there for 20 years? Well, if you take 100,000 gallons of dry cleaning fluid, which even sounds like a lot, and you calculate the solar model predicts that they're only going to see 1.5 atoms turn into argon every day. Now that's a hard experiment to do. You're trying to find one atom in 100,000 gallons of dry cleaning fluid. Now the process alone of figuring out whether you have the atom is very hard, and I'm not going to go into that. But the number's pretty small, and that's because the interaction probability that I told you about is so very, very small. Even though there are many, many solar neutrinos predicted, and there are many, many atoms of chlorine, you multiply all the numbers together, and the theory tells you, too bad, you're still only going to see 1.5 a day. So these guys sort of set up for the long haul. They went down there and they set up camp. I was watching a video, and matter of fact, if anybody has an opportunity to watch The Young Explorers with Bill Curtis, it's on public television, he does a lecture about this, and he talks about this exact experiment with a lot more pizzazz than I can do. But the interesting thing was they set up down there, but remember they're a mile underground. They have no running water. They have no flush toilets. It's a hard life, and the elevator only goes up and down once a day. So I decided that was not an experiment that I really wanted to work on. But the fun thing about it is they did it, and they took their data. Remember I told you they've been doing this for 20 years, and each of these dots is the number of atoms per day of chlorine that they measured, they actually detected. Remember, this is the number that the solar model predicted. So what do you see? It's really low. Now remember I said, well, even if you were off by a factor of 2 in the number of neutrinos coming from the sun, that's still a lot of neutrinos, and it sure is. But the interesting thing is that the fact that this data for 20 years is consistently more than a factor of 2, it's almost a factor of 3 below what the model predicts, really has the scientists wondering. Now, there are 2 reasons that this could happen, okay? Well, there's actually 3. And I'm going to pose the question, or at least this is the question that I would ask. I could ask, where are the missing neutrinos? Or you might ask, are there missing neutrinos? Because you don't believe in neutrinos anyway, right? Now, there's another reason that they could be missing. Remember I showed you the complicated solar model. Maybe the solar model is wrong and there just shouldn't be that many neutrinos. Well, it turns out this has got a lot of attention of particle physicists because either the solar model is wrong or there are no neutrinos, which many other fields of particle physics have sort of validated that the neutrino does exist, or there are missing neutrinos. Something is happening to the neutrinos from the time they leave the sun until they get to the Earth. Now, I think the really exciting question is the first one. What is happening to the neutrinos? Where are they going? Now, remember I showed you that the new periodic table, or the arrangement of quarks and leptons. This was the real world, the up, the down, quark, an electron, and electron neutrino, a neutrino that went with the electron. And I told you that there were these other cousins of the electron, and they have these neutrino pairs. Well, what's being hypothesized, it's actually an idea that's been around for, not quite 20 years, but almost, is that those neutrinos from the sun, that's just these, maybe they don't always stay electron neutrinos, but that there's more complicated interactions between the neutrinos, and that an electron neutrino can become a muon neutrino, or a muon neutrino, if you created one, could become a tau neutrino. Now, that's an interesting thing. It sort of destroys the beauty of what we believe is the real world and the world you create at high energy. But physicists like to think of strange things and strange answers beyond a model that maybe seems perfect but has a few little glitches. And this can happen if the neutrino has a mass. Now remember, in the beginning we hypothesized that the neutrino existed as a particle that had no mass. But the only way to explain the missing neutrinos from the sun is, well, one of the ways, the one that I sort of as a particle physicist want to believe in, is that the neutrino actually does have a mass. It's not quite as mysterious as someone might want to say if it was massless, but it's very, very small. Well, given what we told you about the number of neutrinos from the sun and how hard it is to detect them, if I were you, I guess I would ask 2 more questions. Like, how small of a mass are you talking about? And even if I told you how small I was talking about, how would you ever be able to tell? Okay? And what I'm going to sort of finish up with is the experiment that I'm working on. And that is at my accelerator at Fermilab. I'm going to take a proton beam out of the accelerator. I'm going to send it into the ground where I'm going to hit a target. In that target, we're going to make lots and lots of particles. Yes, protons and neutrons and other strange things. Also particles called pions. They're actually lighter than protons. Story of the Homestake gold mine, which sounded really neat. This is just iron ore. And he says, oh, yuck, that's boring. But it's a mine. It's a half a mile underground. It's not quite as far underground. But there's a detector in there. And the reason there's a detector there is because about 10 years ago, some physicists also had the bright idea that although the proton seems pretty basic and it makes up the world around us, maybe protons decay just like other things, like neutrons and so on. So they built a very, very large detector made out of many, many protons, like 10 to the 30th protons, and looked for protons to decay. Well, they didn't see any, so that means we're pretty safe for a while. I think they decided the lifetime, that experiment says the lifetime of a proton is more than 10 to the 31 years. So, you know, we don't have to worry about protons decaying. But the fact is that that detector sitting down there is so big, because it was big, it made a lot of protons because we wanted to see protons decay. It can also be used as a neutrino detector. So the idea is, if you knew how many neutrinos you produced here, and you went up there and counted how many neutrinos, you could calculate, just like the solar experiment. You can predict how many neutrinos. If all these neutrinos stay the same and nothing happens to them on the way to Minnesota, then you should be able to count the number of neutrinos you see there. And if you see fewer neutrinos than you expected, then you'll know that indeed those neutrinos decayed or changed into some other kind of neutrino. Okay? Now, the ability of a neutrino to change from one type of neutrino to another is only possible if it has a mass. And over this distance, there's a formula that you can calculate, that over this distance, if the neutrino decays, it has a mass of about 1 electron volt. Now, what does that mean? An electron has 500 million electron volts of weight, and a proton has 900 million electron volts. Pardon? 500.5 MeV, right. So, yeah, 500,000. The electron is 2,000 times lighter than a proton, but the neutrino I'm talking about is 1,000,000 times lighter than an electron. So it's very, very small. So we don't ever have to worry about those neutrinos from the sun passing through us and doing anything. They're still very, very small. But the idea is that the hypothesis that we started with, that the neutrino was chargeless, it's still going to be chargeless, but is also massless, may not be true. But the only way we find this is by probing literally deeper and deeper, or farther and farther. Okay. So that's a project that's going on at Fermilab, or trying to go on at Fermilab, and it's actually quite exciting and quite revolutionary. Okay, so now I want to finish up saying, go back to our puzzle. Did anybody figure out the puzzle? Anybody who figured it out, don't tell us the answer if you actually read it in a book before you came here. No? Oh, up there, okay. You want to stand up and tell us? You can't really tell it? Can you describe it?
Not really.
Oh, okay. Does anybody else want to take a stab at it? Okay, over here.
I think the squares always connect to exactly two other shapes, and the triangles can connect to anything.
Okay. That's almost there. Those are some rules. The triangles can connect. Does anybody want to take another stab? A little more complete? Over here?
There are no observed squares and triangles, though. Is that not correct?
Pardon?
There are no observed squares and triangles.
Correct.
So, therefore, you can't have it. I think that the whole thing is made up of the little diamonds put together,
Okay.
one after the other.
Okay. Almost. Okay. One more. Okay, one more.
Basic shapes are a square and a triangle. A square must always touch two other shapes. A triangle can only touch one other shape.
Okay, that's pretty close. That's pretty close. Now, there are answer sheets somewhere. If you want to take them home to do your friends to remember. Okay, I guess Steve has them in the back. Let me just put up here the way they described the solution here. I think we were really close with those answers. Okay, the basic shapes, or the basic building blocks of these, are the triangle and the square. Okay, so that's when we're looking for what are our basic building blocks of matter. We identify something very small, smaller than what we actually observed, because remember we saw diamonds, but a diamond is really made up of the triangles. And we saw these larger objects made up of squares and triangles. Now, what are the rules? The rules are that the triangles must connect on one and only one side. Now, why is that? Because if they connected on more than one side, you could make this. Remember, what you couldn't see was a big triangle, or just a triangle alone. Okay? And the squares, you never just saw a square connected on one side. The squares are always connected on at least two sides. Okay? So you observe some things, you never see certain things, and by never seeing certain things, you can deduce some of the laws. Okay? Anybody have any questions they want to ask in particular? If not, thank you very much for your attention.